Hello and welcome. We are going to solve one more problem on the working of magnetic forces. You can see there is a problem at your screen heading magnetic forces and a rolling hoop. So let us read the statement of the problem and see what's going on. The problem statement is simply small balls of charge Q are attached to point here, I guess, and here, and attached to points P1 and P2. Okay, and P1 and P2 are here of a ring made of insulating material, dielectric, moving in a vertical plane at an angle alpha equals 60 degree. Okay, this angle is 60 degree. The ring is in a homogeneous magnetic field of induction B. The lines of force of which are perpendicular to the plane of the ring. You can simply see here, and the ring is moved so that it rolls without slipping. So it's a case of rolling without slipping on a horizontal surface made of insulating material again. And the speed of its center is V naught. Yeah, you can see it here. What is the magnitude of magnetic force acting on each charged balls in the positions shown in the figure? Yeah, in this position, we have to find out the magnitude of magnetic force acting on each charged ball, and then in which positions of the loop is there no torque of the resultant of the magnetic forces with respect to the center of the hoop. So this problem is something else, asking about torques. In which of these positions does the magnetic force exert a greater force on the hoop? That means we are considering more than one positions. And what is this force? So we have to be a bit careful. And next problem is determine the point of intersection of the lines of action of the magnetic forces. I think each of the problems need a special attention. So though I've already solved this problem and drawn a picture for this, so the first problem is finding the force on the balls. So I'm going to try the idea that the force acting on the ball of charge Q, of course, moving in a magnetic field with some velocity v, which is of course perpendicular to both the velocity vector and magnetic induction vector, the force itself, because it's qb cross b. So the force will be perpendicular to both the vectors, velocity vectors and magnetic field vector, and its magnitude will be simply qbb. In this, we have taken advantage of the fact that magnetic field and velocity are perpendicular to each other. Magnetic field is basically perpendicular to the plane of the rolling wheel, and their velocities, of course, is in this plane of the rolling wheel. So magnetic field is of course perpendicular to the velocity of the balls, and for the sake of clarity, I have just drawn a picture you would like to see here. picture is something like here at your screen. You can see here that we have the magnetic field, like in this direction. The charge at this point will have a velocity v1. Uh, we are going to discover that this v1 will be equal to 2v0 pretty soon, and then the ball 2 has velocity equal to v2, and what can be the value of v2 we are going to find out, and find out how. That is simple. How can we find out each of the things is pretty simple. And so let's work out and try to find out. The velocity of the balls can be thought of superposition of horizontal velocity v0, this thing, of the center of the circle, and tangential velocity of pure rolling, that is also v0. And if we can write this v0 equals simply r omega, and p1 is here, and it is at the top of the rolling wheel, so its velocity v1 can be simply 2v0. We know from our prior experience of working with such kind of problems. And to find the value of v0, the velocity of point P2, which is here, we can consider this picture, and this is the velocity of this particle here at P2. And if you can find it, which is very a small thing to find, and you have certainly found out in your previous courses of rolling, and it will come out simply as root 3 v0. So the forces in question are being solved. Force on this P1 can be written as F1, and it will be simply QBV1, that is 2QBV0, of course, and F2 you are going to find out, this will be simply QBV2, and that is root 3 QBV0. So no problem at all. First part of the problem has been solved. Now if we can solve the second part, and the second part of the problem was nothing but let me see again this picture to find out what was the second part of the problem actually. By which position the hoop in their positions of the hoop in there is there no torque, in which positions of the hoop is there no torque on the resultant of the magnetic forces with respect to the center of the hoop, and the positions will come out more than one. So the problem is asking in which position the force will be greater, and we have to find out the magnitude of the force as well. So let's put it down somewhere. And let's try to solve this problem again to find out the torques. And I have a picture and I'm going to solve it pretty soon once I clear this screen and bring the picture meant to solve the purpose. Here we have another picture on the screen and start with the thought that the velocity vector of any point of the ring can be obtained as sum of two vectors. One is the velocity of the center, which was given as simply as V naught, and one the circumferential velocity or the tangential velocity, being in pure rolling, arises due to the rotational motion of this. It can be anywhere, like here it is again V naught and here it is tangential and V naught, and the magnetic force acting on the charged body attached to the ring can also be obtained as the vector sum of the magnetic forces belonging to the individual velocity components. I'm using superposition principle. So consider the position of the ring in which I think we need to consider the position of the ring in which the ray belonging to P2 makes an angle phi with the vertical. You can see it here. And while the ray belonging to P1 lags behind by an angle alpha, both angles are arbitrary, so that this angle becomes alpha minus pi. That means this angle is not alpha, but rather this whole angle is alpha, so that this angle is alpha minus phi. It is just nothing is known here, not alpha, not phi. We are just considering things, and let's find the value of phi at which the resultant force has no torque with respect to the center O of the ring. And for this you can see here that this force FC1, this force, and FC2, this force, they correspond to the tangential velocity. B is in this direction, and you can accordingly show that the F2C will be along the radius, because the magnetic force is perpendicular to the velocity, and if velocity is tangential, then the magnetic force obviously will be radial. So these two forces are radial. Of course, both of them are radial, and they produce no torque about point O. F1C and F2C, they produce no torque about point O, the center of the ring, and the Lorentz force corresponding to the horizontal velocity, this is vertical. These two forces are vertical, and they will have same magnitude, because F1F or whatever we would like to write it will be QB V naught, And in the similar manner, F to F can also be written as Q B B naught. So both forces have same magnitude and same direction. And now we can think one thing: the resultant of the forces will have zero torque if the corresponding levers, that is K1 and K2, are equal. And we got the condition that K1 and K2 drawn in this picture are the levers of the forces, and they should be same if there should be no torque, zero torque on the ring. And that you can say, that you can write here, that means if K1 and K2 are equal, this is basically K1 and this is basically K2. And if you can consider the right angle triangles here, you can write, if K1 is equal to K2, then sine alpha minus phi must be equal to sine phi. And then alpha, you know, is given equal to 60 degree. And do some trigonometric transformation, and you will find that tan alpha, it means tan alpha by 2 equal to tan phi. And that means phi is simply equal to alpha by 2, that is 30 degree. And this can also be considered that if this phi is equal to 100 plus alpha by 2, 100 degree alpha, if you are not forgetting it, alpha is this angle. So if we are taking this case in which phi is 180 degree plus alpha by 2, that is equal to 210 degrees. In both positions, the ball are symmetrically arranged with respect to the vertical diameter of the hoop, of course. And velocity is greater in upper position than the lower position. So the force will be greater in the upper position, that is 30 degree position, where phi equals 30 degree. And of course, in the lower position, it will be smaller. So I think this problem we solved as well. But here comes the third problem, that is third part of the problem, and that is difficult. So let me clear the screen first, and then I'm going to solve it. Now, so I need to clear it by using the remover itself, and then I'm going to explain. But first we need to find what the problem is. So I'm going to get this picture back on the screen so that I can read the picture. The third part of the problem says, determine the point of intersection of the lines of action of magnetic forces. Okay. We will try to find that. And I have solved this problem previously, so I have drawn a picture for it. I'm going to consider the case again, but this picture seems appropriate, so let me find the real picture. So you can now rightly see the picture at your screen. And I have considered the position of the hoop in which ray down to P1 makes an angle phi with the vertical, and ray corresponding to P2, of course with respect to center, you can see it here, it makes an angle phi plus alpha. Alpha is this angle, phi plus alpha with the vertical. So these are two positions, and with vertical, this P1 ray for P1, that is OP1, makes an angle phi with vertical, and that with P2, that is OP2, makes an angle phi plus alpha. And we saw that the point of intersection P3 of this forces acting on this charge particle P1 is in this direction and P2 is in this direction. I've shown the pictures because how we did in this, you need to learn something. The force, the magnetic force and P1 is the force on P1 acts due to two reasons. One due to this horizontal velocity, and due to this force, due to this velocity, the magnetic force acting on this will be in vertically upward direction. And so this force, the component of force acting on P1 as a vertical component here, and on P2 it is also vertical and the force component is here. And the second force is radial, second magnetic force is radial. From here, for P2, the force is radial like this, in the direction of OP2 itself. And the magnitude of both these forces, because this force arises also due to this force is also QB0, and this force is also QB0, and same goes with these two forces as well. So the resultant of these two forces will be bisecting the parallelogram made by these two forces, and so is done by this resultant force at this resultant magnetic force acting on P1. So you don't need to worry much about these things, this diagram, and we should work fine here by thinking about the point of intersection of these two resultant forces. This force and this force. And we just shown in the picture the point of intersection P3 and this point of the lines of action of magnetic forces acting on point charges, coinciding with not coinciding with the contact force, with the contact point P here. The figure is deliberately slightly distorted so that the statement, because I know that this P3 will be simply point P, but the figure is slightly distorted, so that a statement to be proved is not read from the correct figure without justification. We need to justify it first. So we are going to take advantage of few facts. And first, let us take advantage of the fact that two components of the magnetic forces acting on each point charge are equal. Two components, these two components and these two components are equal. So their resultant bisects the angle phi, which is here, angle phi here. If this angle is phi, this angle is also phi, because this line is radial, and angle phi between them. And you can find one thing that is obvious. Here, this angle, you can see that this angle, this angle 2 gamma, it is equal to 2 gamma is definitely equal to phi plus alpha. Why? You know yourself. This is the common line between, this is a line OP2, and this angle is 2 gamma that is made with a vertical, and there is a vertical line, and the same line makes an angle alpha plus pi. So 2 gamma is going to be equal to phi plus alpha here. So if you can see the picture, you will find it yourself that this thing is going to happen here. And at the same time, the triangle OP1 P2, it is isosceles, no doubt. Both are radii of the circle, so these two angles are same. And from the consideration of this triangle OP1 P2, you can write here alpha plus 2 beta is equal to 180 degree. And so you can write here beta is equal to 180 degree minus alpha by 2. Yeah, like this. So we have in information a relation between angle beta shown in the picture and angle alpha, and this is going to be 180 degree minus alpha by 2. So I'm moving to another fact, because we are going to discover many more facts here itself. And also we know that the sum of interior angles of triangle, and we have one more relation. In fact, we had one more relation, this one. This is relation 2, and the relation 1 was 2 gamma equal to phi plus alpha. We already knew that. And now we are going to consider another fact. The sum of interior angles of triangle P1, P2 and P3. P1, P2 and P3. The triangle is this. P1, P2 and P3 is equal to 180 degree, no doubt. So we are going to write 2 beta plus gamma plus delta equal to 180 degree. And oh no, this angle is not beta. Sorry, I made a mistake here. Well, this angle is beta plus gamma. This angle is beta plus gamma, but this angle is beta minus pi by 2. So I would like to write beta minus pi by 2 plus beta plus gamma. Beta plus gamma is this angle, and this angle is delta equal to 180 degree. Yeah. And beta is simply 180 degree minus alpha by 2 and minus pi by 2 as well, and plus 180 degree minus alpha by 2, again beta is here, plus gamma. Gamma is phi plus alpha by 2, and that is pi by 2 plus alpha by 2, and plus delta, and it is equal to 180 degree. And solve this. You will simply get that delta is equal to alpha by 2. And then you know the most important thing here, that disk arc is putting an angle equal to alpha at the center of the circle, and this arc is going to put an angle here at P3 equal to alpha by 2. That means we all know that P3 should be at P. P3 is not here, rather it is here. And we all know from the angles subtended by an arc at the center and at a point on circumference, they hold the relationship of if an arc subtends an angle alpha at a point on circumference, then the same arc is going to subtend an angle 2 alpha at the center of the circle. And this provides us the clear-cut insight that P3 should not be here but at point P. So that means what I am trying to tell you, that if the arc P1, P2 subtends an angle alpha at the center of the circle, then they will subtend an angle alpha by 2 at any point on the circumference of the same circle. And that proves the point P3 is located on the circle, precisely at the lower end point of the vertical diameter of the circle. And it solves our problem. So thank you very much for watching.